Database normalization is a fundamental process in database design that transforms how we organize and structure data. It's the systematic approach to arranging data in a database to achieve optimal efficiency and maintain data integrity. Database normalization is the systematic process of organizing data in a database to minimize redundancy and eliminate dependency issues, while ensuring data integrity and consistency throughout the system. Consider this unnormalized student courses table. Notice how student names are repeated multiple times and course information is duplicated across rows. This redundancy creates several serious problems that normalization addresses. Normalization has three primary goals. First, minimize data redundancy by eliminating duplicate information storage. Second, eliminate dependency issues by removing problematic data relationships. Third, ensure data integrity by maintaining accuracy and consistency throughout the database. Unnormalized databases suffer from three critical data anomalies. Insert anomalies prevent adding data without unrelated information. Update anomalies require changing multiple locations for a single logical change. Delete anomalies cause loss of important data when removing unrelated records. Normalization eliminates these problems. Normalization is crucial for reliable data management because it ensures data consistency by maintaining a single source of truth. It improves storage efficiency by reducing redundant data and enhancing performance. It simplifies maintenance by making updates and modifications easier to manage. Most importantly, it preserves data integrity by preventing inconsistencies and data corruption that can compromise business operations. Database normalization forms the foundation of effective database design. By systematically organizing data to eliminate redundancy and dependencies, normalization creates robust, efficient, and maintainable database systems that support reliable business operations and data-driven decision-making. Data anomalies are fundamental problems that occur in poorly designed databases. These anomalies create inconsistencies, data loss, and maintenance nightmares. Understanding these core problems is essential before we can appreciate why normalization is so important. The insertion anomaly occurs when you cannot add certain data to your database without being forced to include unrelated or unknown information. This creates artificial dependencies between different types of data. Consider this poorly designed student enrollment table. To add a new course to the system, we must also provide student enrollment data. But what if we want to add a course that no students have enrolled in yet? We cannot do it without creating fake student records. Now watch what happens when we try to add a new course called Machine Learning, taught by Dr. Wilson. We cannot insert this course information without also providing student data, even though no students have enrolled yet. This forces us to either create fake student records or delay adding the course until someone enrolls. The update anomaly occurs when the same piece of information is stored in multiple places, requiring multiple updates to maintain consistency. If you miss updating even one location, your data becomes inconsistent and unreliable. Look at this table where instructor information is repeated for each student enrollment. Dr. Smith teaches the database course, and this information appears in multiple rows. What happens if Dr. Smith gets replaced by Dr. Johnson? We need to update Dr. Smith to Dr. Johnson in all three locations. But what if we accidentally miss one? We end up with inconsistent data, where some records show Dr. Smith and others show Dr. Johnson for the same course. This creates confusion and unreliable information. The deletion anomaly is perhaps the most dangerous of the three. It occurs when deleting a row causes you to lose important information that should be preserved. This can result in permanent data loss that cannot be recovered. Consider this scenario. We have course information mixed with student enrollment data. Each row contains both student details and course details. What happens if the last student drops out of a course? Alice is the only student enrolled in the Advanced AI course. If Alice drops out and we delete her enrollment record, we lose all information about the Advanced AI course itself, its course ID, name, and credit hours. This valuable course information disappears from our database permanently. These three data anomalies create serious problems in database systems. They lead to data inconsistency, information loss, and maintenance difficulties. Understanding these problems is crucial because normalization techniques are specifically designed to eliminate these anomalies and create more reliable database structures. First normal form, or 1NF, is the foundation of database normalization. It establishes the basic rules that every relational database table must follow to be considered properly structured. First normal form has four fundamental requirements. Each cell must contain atomic values that cannot be divided further. Each column must contain values of the same data type. Every row must be unique, and the order of rows should not affect the data's meaning. Let's examine a practical example to understand how these requirements work in practice. Here we see a student enrollment table that violates first normal form. Notice how the courses column contains multiple values separated by commas, and the phone numbers column also contains multiple phone numbers in single cells. These violations make it difficult to query specific courses or phone numbers. We cannot easily search for students taking a particular course or efficiently manage multiple contact numbers. Now let's transform this table to comply with first normal form by eliminating these repeating groups. In the normalized version, each cell now contains atomic values. Each course is in its own row and each phone number is in its own row. This creates more rows, but each cell contains only one indivisible piece of information. Now we can easily query for students taking specific courses, efficiently manage contact information, and perform database operations without parsing complex cell contents. Let's summarize the key benefits of achieving first normal form. First normal form eliminates repeating groups, simplifies data access, enables efficient querying, provides the foundation for higher normal forms, and ensures data consistency. While it may increase the number of rows, it creates a solid foundation for relational database operations. First normal form is the essential first step in database normalization. Every well-designed relational database must achieve 1NF before progressing to higher normal forms. Second normal form, or 2NF, builds directly upon first normal form by addressing a specific type of dependency problem called partial dependencies. To understand 2NF, we must first understand what makes a dependency partial. The key to understanding 2NF lies in composite primary keys. A composite primary key consists of two or more attributes that together uniquely identify each row. Partial dependencies occur when a non-key attribute depends on only part of this composite key, rather than the entire key. Let's examine a concrete example that violates 2NF. This student enrollment table has a composite primary key of student ID and course ID. However, notice that student name depends only on student ID and course name depends only on course ID. These are partial dependencies because these attributes don't need the entire composite key to be determined. Now let's visualize these partial dependencies. Student name has a partial dependency on student ID only, ignoring course ID. Similarly, course name has a partial dependency on course ID only, ignoring student ID. These partial dependencies create data redundancy and potential inconsistencies. To achieve 2NF, we must eliminate these partial dependencies by decomposing the table. We create separate tables where each non-key attribute is fully dependent on the entire primary key of its table. This process removes redundancy and prevents update anomalies. Here are the resulting 2NF tables. The students table contains student ID and student name, where student name is fully dependent on student ID. The courses table contains course ID and course name, where course name is fully dependent on course ID. The enrollments table maintains the many-to-many relationship with grade fully dependent on both student ID and course ID. Achieving 2NF provides significant benefits for database design. It eliminates data redundancy by removing partial dependencies, prevents update anomalies where changing one piece of information requires multiple updates, and ensures that each piece of data has a single, authoritative location in the database structure. Third normal form, or 3NF, builds upon second normal form by addressing a specific type of dependency problem called transitive dependencies. Understanding and eliminating these dependencies is crucial for creating well-structured databases. Third normal form has two key requirements. First, the table must already be in second normal form, meaning it has no partial dependencies. Second, and most importantly for 3NF, there must be no transitive dependencies present in the table structure. A transitive dependency occurs when a non-key attribute depends on another non-key attribute rather than directly on the primary key. In this diagram, attribute C depends on the primary key A, but only through attribute B. This creates an indirect or transitive dependency that violates third normal form. Let's examine a concrete example. Here we have an employee table that contains employee information along with department details. Notice that department name and location are stored with each employee record, creating redundancy and potential transitive dependencies. The problem becomes clear when we analyze the dependencies. Department name and department location depend on department ID, not on employee ID. This creates a transitive dependency. Employee ID determines department ID, and department ID determines department name and location. The normalization process begins by identifying the transitive dependencies. In our example, employee ID determines department ID, and department ID determines both department name and department location. This chain of dependencies violates third normal form. The second step involves decomposing the original table into separate tables to eliminate the transitive dependencies. We create one table for employee information and another for department information. After normalization, we have two separate tables. The employee table contains only employee-specific information with a foreign key reference to the department. The department table contains all department-related information. This eliminates the transitive dependency and achieves third normal form. This normalized structure provides several key benefits. It eliminates data redundancy since department information is stored only once. It prevents update anomalies because changes to department details need to be made in only one place. Most importantly, it ensures that all non-key attributes depend directly on their respective primary keys, satisfying third normal form requirements. Voice Code Normal Form, or BCNF, represents a stricter version of third normal form. While 3NF eliminates transitive dependencies, BCNF goes further by addressing a specific problem that can occur when tables have overlapping candidate keys. To understand BCNF, we first need to clarify two important concepts: determinants and candidate keys. A determinant is any attribute or set of attributes that uniquely determines other attributes in a table. A candidate key is a minimal set of attributes that can uniquely identify every row in the table. The problem BCNF solves occurs when a table has multiple overlapping candidate keys. This can create situations where a table is in 3NF but still contains anomalies. Let's examine a concrete example to illustrate this issue. Consider this student course instructor table. Each student can take multiple courses, each course can have multiple instructors, but each student course combination has exactly one instructor. This creates overlapping candidate keys: student ID plus course ID, and student ID plus instructor ID. This table has two candidate keys. The first candidate key is the combination of student ID and course ID, which uniquely identifies each row. The second candidate key is student ID and instructor ID, which also uniquely identifies each row since each student has only one instructor per course. The BCNF violation occurs because instructor ID determines instructor name, making instructor ID a determinant. However, instructor ID by itself is not a candidate key. It cannot uniquely identify all rows in the table. This violates the BCNF rule that every determinant must be a candidate key. To convert this table to BCNF, we need to decompose it into multiple tables. We separate the problematic dependency by creating a dedicated instructor table and modify the main table to remove the redundant instructor name information. Now both tables are in BCNF. In the student course instructor table, the candidate key is student ID plus course ID, and there are no other determinants. In the instructor table, instructor ID is both a determinant and the candidate key, satisfying the BCNF requirement. While BCNF provides the highest level of normalization for eliminating anomalies related to functional dependencies, it comes with trade-offs. Achieving BCNF may require more table joins for queries and can impact performance. However, it ensures maximum data integrity and eliminates all anomalies caused by overlapping candidate keys. Fourth normal form, or 4NF, addresses a specific type of dependency problem that can occur even in tables that are already in Boyce Codd normal form. Understanding 4NF requires us to first understand what multi-value dependencies are and why they create problems in database design. For a table to be in fourth normal form, it must satisfy two key requirements. First, the table must already be in Boyce-Codd normal form, meaning all functional dependencies have been properly addressed. Second, the table must not contain any multi-valued dependencies. A multi-valued dependency exists when one attribute determines multiple independent sets of values. The key word here is independent. For example, a student may be enrolled in multiple courses and have multiple hobbies, but these two sets of information are completely independent of each other. Here we see a table that violates fourth normal form. Notice how Alice takes both math and physics courses and has both reading and swimming as hobbies. The problem is that every combination of course and hobby must be stored, even though courses and hobbies are completely independent of each other. This design creates a Cartesian product problem. If Alice has 2 courses and 2 hobbies, we need 4 rows. If she adds another course, we need 6 rows. If she adds another hobby, we need 8 rows. The storage grows exponentially, and courses and hobbies are artificially linked when they should be independent. The solution is to decompose the original table into 2 separate tables. The student courses table stores the relationship between students and their courses, while the student hobbies table stores the relationship between students and their hobbies. This eliminates the multi-valued dependency. This decomposition provides several key benefits. First, we eliminate redundant data storage. Second, courses and hobbies are now stored independently as they should be. Third, the tables are easier to maintain and query. Finally, we eliminate update anomalies that could occur when trying to modify course or hobby information. To detect multi-valued dependencies in your tables, follow these steps. First, identify attributes that can have multiple values for a single key. Second, check if these multi-valued attributes are independent of each other. Third, look for Cartesian product patterns in your data where every combination appears. Finally, verify that changing one attribute doesn't logically affect the other. In summary, fourth normal form eliminates multi-valued dependencies by requiring decomposition into separate tables. This prevents the Cartesian product data explosion that occurs when independent multi-valued attributes are stored together. The result is a database design that maintains data independence and integrity while eliminating unnecessary redundancy and update anomalies. Fifth normal form, or 5NF, represents the highest level of normalization commonly discussed in database theory. It requires that a table already be in fourth normal form and addresses a very specific type of dependency called join dependencies. Fifth normal form has 4 key requirements. The table must already be in fourth normal form, meaning all multi-valued dependencies have been eliminated. The table cannot be decomposed into smaller tables without losing information. It must eliminate all join dependencies, and it achieves the maximum possible decomposition of the data. Join dependencies are fundamentally different from functional or multi-valued dependencies. A join dependency occurs when a table can be split into multiple smaller tables, but the original table can only be perfectly reconstructed by joining all of the split tables together. This creates a complex web of relationships that must be preserved simultaneously. Consider this example table that tracks project assignments, employees, and their skills. This table appears to be in fourth normal form, but it contains a hidden join dependency. The relationship between projects, employees, and skills cannot be properly represented without all 3 attributes together. The problem becomes clear when we try to decompose this table. If we split it into just 2 tables, one for project-employee relationships and another for employee-skill relationships, we lose critical information. When we join these 2 tables back together, we get false combinations that weren't in the original data, such as Alice having JavaScript skills on the database project. The fifth normal form solution requires decomposing the table into 3 separate tables: project employee, employee skill, and project skill. Each table captures one specific relationship. Only by joining all 3 tables together can we reconstruct the original data without any false combinations or information loss. Despite its theoretical importance, fifth normal form is rarely applied in practice for several compelling reasons. The complexity of identifying and managing join dependencies is extremely high. Performance suffers because even simple queries require complex multi-table joins. Maintenance becomes significantly more difficult with 3 or more tables instead of 1. Most importantly, join dependencies are quite rare in real-world scenarios, and the benefits rarely justify the added complexity. The key takeaways for fifth normal form are these. It eliminates join dependencies through maximum decomposition, requiring all decomposed tables to be joined together to reconstruct the original data. While it provides theoretical completeness in normalization, it has significant practical limitations. Most real-world databases stop at third normal form, or Boyce-Codd normal form for practical reasons, as these provide the best balance of data integrity and usability. Understanding which normal form to apply in practice requires balancing database integrity with implementation complexity. Different normalization levels serve different purposes and have varying degrees of practical necessity. The first two normal forms, 1NF and 2NF, are fundamental requirements that should always be implemented. These forms eliminate the most basic data anomalies and establish the foundation for relational database design. Third normal form represents the standard target for most database applications. It provides an excellent balance between data integrity and practical implementation, eliminating transitive dependencies while remaining manageable for most development teams. Boyce-Codd normal form should be applied specifically when overlapping candidate keys exist in your database design. This is a more specialized scenario that requires careful analysis of key relationships and dependencies. Fourth and fifth normal forms are reserved for highly complex scenarios involving multi-valued dependencies and join dependencies. These are rarely needed in typical business applications and should only be considered for specialized data modeling requirements. To help you choose the appropriate normalization level, consider this practical decision framework that guides you through the key questions and considerations for each normal form. Start by ensuring your database meets the fundamental requirements. First normal form eliminates repeating groups and ensures atomic values. Second normal form removes partial dependencies on composite keys. These two levels are non-negotiable foundations. For most applications, third normal form represents the optimal target. It eliminates transitive dependencies while maintaining practical implementation complexity. This level provides excellent data integrity for typical business scenarios. Consider Boyce-Codd normal form only when you have overlapping candidate keys in your design. This requires additional analysis, but resolves specific anomalies that 3NF cannot address in these particular scenarios. Fourth and fifth normal forms should only be considered for highly specialized scenarios with complex multi-valued or join dependencies. These are rarely encountered in typical business applications and require advanced database design expertise. Here are the key practical guidelines to remember when choosing your normalization level. These recommendations are based on real-world database design experience and industry best practices. Always implement first and second normal forms as your baseline. These eliminate the most critical data anomalies and establish proper relational structure. No database should operate below these levels. Target third normal form for most business applications. This level provides excellent data integrity while remaining practical to implement and maintain. It handles the majority of real-world scenarios effectively. Apply Boyce-Codd normal form only when you identify overlapping candidate keys in your design. This requires additional analysis but resolves specific anomalies that third normal form cannot address. Reserve fourth and fifth normal forms for truly complex scenarios with multi-valued or join dependencies. These are specialized cases that require advanced expertise and are rarely encountered in typical business applications. De-normalization represents a fundamental shift in database design philosophy. While normalization seeks to eliminate redundancy, de-normalization deliberately introduces it for strategic purposes. De-normalization is the intentional introduction of redundancy into a database structure. Unlike normalization, which eliminates redundancy, de-normalization strategically adds it back to achieve specific performance or business goals. This approach represents a strategic trade-off between data integrity and system performance. By accepting some redundancy, we can significantly improve query speed and reduce system complexity. Denormalization is particularly valuable in read-heavy systems where query performance is more critical than write efficiency and where the benefits of faster reads outweigh the costs of maintaining redundant data. Denormalization involves a careful balance between competing priorities. On one side, we have data integrity with its benefits of consistency and storage efficiency. On the other side, we have performance benefits, including faster queries, reduced complexity, and improved scalability. Denormalization tips this balance toward performance when the strategic benefits justify the trade-offs. Let's examine the structural differences between normalized and denormalized approaches. In a normalized database, we maintain separate tables with relationships, requiring joins to retrieve complete information. In contrast, a denormalized structure combines related data into a single table, introducing redundancy but eliminating the need for joins. Notice how customer names are now duplicated, but queries become much simpler and faster. Denormalization is a strategic decision that should be made based on specific system requirements and usage patterns. It's most beneficial in read-heavy workloads where query performance significantly outweighs update frequency. Performance-critical applications, such as real-time analytics or high-traffic web applications, often benefit from denormalization when response time is more important than storage efficiency. Systems with complex queries requiring multiple joins are prime candidates for denormalization. By pre-joining data, we can dramatically reduce query complexity and execution time, making the system more responsive and scalable. Understanding denormalization as strategic data redundancy helps database designers make informed decisions about when to prioritize performance over perfect normalization, creating systems that better serve their intended purpose. Denormalization becomes beneficial in specific scenarios where the advantages of data redundancy outweigh the costs of maintaining normalized structures. Understanding these scenarios is crucial for making informed database design decisions. Read-heavy workloads are characterized by a high ratio of query operations compared to data modifications. In systems where 90% or more of operations are reads, denormalization can significantly improve performance by reducing the need for complex joins. When reads vastly outnumber writes, the performance penalty of maintaining redundant data becomes negligible compared to the speed gains from avoiding joins. This is common in content management systems, product catalogs, and user profile systems. Complex joins involving multiple tables can severely impact query performance, especially as data volume grows. When queries regularly require joining 4 or more tables, denormalization becomes an attractive optimization strategy. By strategically duplicating frequently accessed data across tables, we can eliminate expensive join operations. This is particularly beneficial in e-commerce systems where product information, pricing, and inventory data are frequently queried together. Reporting systems and business intelligence dashboards require fast aggregations across large data sets. These systems often need to display real-time or near real-time metrics, making query performance critical for user experience. Denormalization in reporting systems involves pre-calculating aggregations and storing summary data. This eliminates the need to perform complex calculations on the fly, ensuring dashboards load quickly even with millions of records. Caching layers store frequently accessed computed values to avoid repeated expensive calculations. This form of denormalization is particularly valuable for complex mathematical operations, aggregations, or derived data that would be costly to recalculate on every request. Examples include storing calculated tax amounts, shipping costs, user reputation scores, or recommendation engine results. The cache layer acts as a denormalized buffer between the application and the normalized database structure. Data warehousing represents the most comprehensive application of denormalization principles. OLAP systems prioritize query performance over storage efficiency, using techniques like star schemas and dimensional modeling to optimize analytical queries. The star schema design places a central fact table surrounded by denormalized dimension tables. This structure eliminates the need for complex joins during analytical queries, enabling fast aggregations across large datasets for business intelligence and reporting. These scenarios highlight the key decision factors for denormalization: high read-to-write ratios, performance-critical queries, complex joins, analytical workloads, and acceptable storage costs. Understanding these patterns helps database designers make informed decisions about when redundancy serves the greater good of system performance. Calculated fields represent one of the most common denormalization techniques. Instead of computing values on demand during queries, we store the results of calculations directly in our tables. Consider an e-commerce system where we need to display order totals. In a fully normalized database, order totals must be calculated by summing all order items each time we query the data. Here we have a normalized structure with separate orders and order items tables. To get an order total, we must join these tables and perform calculations every single time. Every query requires joining tables and computing sums. For order 1001, we calculate 2 times 25 plus 1 times 15 equals $65. This computation happens repeatedly, creating performance bottlenecks. The calculated fields technique solves this by storing the computed order total directly in the orders table. We trade some storage space for significantly improved query performance. Now our orders table includes a pre-calculated order total field. Instead of computing sums during queries, we simply read the stored value. This transforms expensive calculations into fast lookups. The performance improvement is dramatic. Complex join operations that might take 50 milliseconds become simple reads taking just 1 millisecond. This represents a 50-fold performance improvement for frequently accessed data. Calculated fields are useful in many scenarios. Let's examine several common examples where storing computed values provides significant benefits. Customer account balances are perfect candidates for calculated fields. Instead of summing all transactions every time we need a balance, we maintain a current balance field that's updated with each transaction. Product ratings demonstrate another common use case. Rather than calculating average ratings from thousands of reviews each time a product page loads, we store the computed average and update it when new reviews are added. While calculated fields offer significant performance benefits, they require careful implementation to maintain data consistency and accuracy. First, you need reliable update mechanisms. Database triggers, application logic, or scheduled batch processes must keep calculated fields synchronized with their source data. Second, consistency becomes critical. Calculated fields can become stale if updates fail. Finally, there's a storage trade-off where you exchange disk space for query performance. To successfully implement calculated fields, follow these essential best practices that ensure both performance benefits and data integrity. Use database triggers for automatic updates to ensure calculated fields stay synchronized. Implement validation checks to catch inconsistencies early. Consider batch updates for complex calculations that might impact performance. Monitor the performance impact of your update operations to ensure they don't create new bottlenecks. Finally, document all calculated field dependencies so future developers understand the relationships. Calculated fields represent a fundamental trade-off in database design: storage space for query performance. They're most effective for frequently accessed data with expensive calculations, but success depends on implementing robust maintenance mechanisms to ensure data consistency over time. Lookup value duplication is a denormalization technique that involves copying frequently accessed lookup values directly into the main table. This eliminates the need for joins when querying common reference data, significantly improving query performance. Let's examine a typical normalized database structure. Here we have a products table containing product information and an orders table that references products through a foreign key. Every time we query order details, we must join these tables to get the product name. Now let's see how lookup value duplication transforms this structure. We copy the product name directly into the orders table. This creates some data redundancy, but eliminates the need for joins when querying order information with product names. The performance improvement is significant. With the normalized structure, every query requiring product names must perform a join operation. With lookup value duplication, we can query order information with product names directly from a single table, eliminating the join overhead. However, lookup value duplication comes with important trade-offs. The main benefit is improved query performance through eliminated joins. But we must consider the costs, increased storage requirements, data redundancy, and the challenge of maintaining consistency when lookup values change. Lookup value duplication is most effective when applied to stable reference data that changes infrequently, such as product categories, status codes, or geographic information. The technique provides substantial performance benefits for read-heavy applications where query speed is more critical than storage efficiency. Summary tables are a powerful denormalization technique that involves pre-calculating and storing aggregated data in separate tables. This approach provides rapid access to analytical information without the need to process raw transactional data every time a query is executed. Consider this raw transactional data from an e-commerce system. Each row represents an individual order with details like date, product, quantity, and price. While this normalized structure eliminates redundancy, generating analytical reports requires complex aggregations across thousands or millions of records. Every time we need monthly sales by product, the database must scan through all transactions, perform calculations, and aggregate results. For large data sets, this process can take minutes or even hours, making real-time analytics impractical. Summary tables solve this problem by pre-calculating and storing these aggregations. Instead of processing raw data every time, we create a separate table that contains the results of common analytical queries. Here's the corresponding summary table. Notice how the data is pre-aggregated by month and product. The total quantities and revenues are already calculated and stored, eliminating the need for complex joins and aggregations during query execution. Summary tables provide several key benefits. Query response times become nearly instantaneous, since no calculations are needed. The database server experiences reduced CPU and input-output load. Analytical queries become much simpler, and users enjoy a significantly better experience with faster reporting. However, summary tables must be kept synchronized with the source data. This typically involves scheduled batch processes that recalculate aggregations periodically, or incremental updates that modify only the affected summary records when new transactions occur. Summary tables are widely used across various domains. In data warehousing, they power monthly and quarterly business reports. E-commerce platforms use them for product performance dashboards. Financial systems rely on them for account balance reporting, and web analytics platforms use them to track page views and user engagement metrics. When implementing summary tables, several factors must be considered. There's additional storage overhead for duplicate data. Maintenance complexity and costs increase with the number of summary tables. Organizations must balance data freshness against performance requirements. Finally, choosing the right aggregation levels is crucial for meeting analytical needs without over-engineering the solution. Historical snapshots represent a powerful denormalization technique that preserves point-in-time data states. Unlike traditional database operations that continuously update records, historical snapshots create frozen copies of data at specific moments in time. The fundamental concept behind historical snapshots is data preservation. While operational databases continuously modify records to reflect current states, snapshots capture and store complete data states at predetermined intervals, creating a historical record that remains unchanged. Let's examine a practical implementation using customer data. Consider a customer table that tracks current customer information, including names, addresses, and account balances. This operational data changes frequently as customers update their information and conduct transactions. Now observe the snapshot creation process. At the end of each month, we create a complete copy of the customer table, preserving the exact state of all customer data at that specific point in time. This snapshot becomes a permanent historical record. The key advantage of historical snapshots becomes apparent when we need to analyze trends over time. While the operational table continues to change, our snapshots provide stable reference points for historical analysis and reporting. Implementation considerations for historical snapshots include storage requirements, as each snapshot consumes additional disk space. Organizations must balance the frequency of snapshots with storage costs and determine appropriate retention policies for historical data. Historical snapshots provide a robust solution for preserving point-in-time data states. enabling comprehensive historical analysis while maintaining the performance and flexibility of operational systems. This denormalization technique proves invaluable for organizations requiring detailed audit trails and trend analysis capabilities. When working with denormalized data, maintaining consistency becomes a critical challenge. Since the same information exists in multiple places, any change must be carefully propagated to ensure data integrity across the entire system. Consider this denormalized customer orders table, where customer information is repeated across multiple orders. If John Smith changes his email address, we need to update it in all 3 locations to maintain consistency. The highlighted customer information appears 3 times. Without proper consistency strategies, updating one instance while missing others creates data inconsistencies that can lead to serious business problems. Database triggers are the first strategy for maintaining consistency. Triggers automatically execute when data changes occur, immediately propagating updates to all related tables. They work at the database level, ensuring consistency regardless of which application makes the change. When a change occurs in the source table, triggers fire automatically, updating all dependent tables in real time. This ensures immediate consistency, but can impact performance during high-volume operations. Stored procedures provide the second strategy by encapsulating all data modification logic within the database. Applications must use these procedures to modify data, ensuring that all business rules and consistency requirements are enforced at every access point. This approach centralizes data modification logic, making it easier to maintain consistency rules and business logic. However, it can create bottlenecks and requires careful design to handle concurrent access efficiently. ETL processes provide the third strategy for maintaining consistency across different systems. These processes extract data from source systems, transform it according to business rules, and load it into target systems, ensuring synchronized data across the enterprise. ETL processes can run on schedules for batch synchronization or be triggered by events for near real-time updates. They are particularly useful for maintaining consistency between different database systems or when integrating with external data sources. Event-driven mechanisms provide real-time consistency through message queues and event streams. When data changes occur, events are published to a message bus, and all interested subscribers receive notifications to update their local data accordingly. This approach enables loosely coupled architectures where systems can react to changes independently. It provides excellent scalability and fault tolerance, though it introduces eventual consistency rather than immediate consistency. Application logic represents the fifth strategy, where consistency is managed within the application code itself. This approach uses transactions to ensure that all related updates either succeed together or fail together, maintaining data integrity through programmatic control. This strategy provides fine-grained control over consistency logic and can implement complex business rules. However, it places the burden of consistency management on developers and requires careful coordination across all applications that access the data. Each consistency strategy offers different trade-offs between performance, complexity, and consistency guarantees. The choice depends on your specific requirements for data freshness, system architecture, and operational constraints. In practice, many systems combine multiple strategies to achieve optimal consistency management. The key is understanding when each approach is most appropriate and how they can work together to maintain data integrity in your denormalized database design. The choice between normalization and denormalization is not arbitrary. It requires careful analysis of 6 critical factors that determine which approach best serves your specific database requirements. The first and most important factor is your query pattern. OLTP systems with complex updates, transactions, and data modifications strongly favor normalization to maintain consistency. OLAP systems, focused on simple reads and analytical queries, benefit from denormalization for faster access. Data volume and access frequency patterns are equally crucial. High update frequency with many concurrent modifications requires normalization to prevent conflicts and maintain integrity. High read frequency with minimal updates benefits from denormalized structures that optimize query performance. Consistency requirements vary dramatically across applications. Financial systems, medical records, and inventory management demand critical accuracy where any inconsistency could have serious consequences. Analytics, reporting, and content management systems can often tolerate acceptable lag in exchange for better performance. The remaining three factors complete our decision matrix. Storage costs influence whether you can afford the redundancy of denormalization. Team expertise determines implementation feasibility. Normalization requires strong SQL skills, while denormalization often needs application-level logic. Finally, maintenance considerations balance long-term flexibility against short-term performance gains. Here is your practical decision framework. When most factors point toward normalization, such as complex updates, high consistency needs, and premium storage constraints, choose normalization. When factors favor denormalization, like simple reads, acceptable lag, and performance requirements, denormalization becomes the better choice. Banking systems represent one of the most critical applications of database normalization. Financial institutions cannot afford data inconsistencies, duplicate records, or anomalies that could lead to incorrect account balances or transaction errors. Banking systems must adhere to ACID properties. Atomicity ensures transactions are all or nothing. Consistency maintains data integrity rules. Isolation prevents concurrent transaction interference. Durability guarantees permanent storage of committed transactions. A properly normalized banking database separates entities into distinct tables. The Customers table stores personal information with a unique customer ID as primary key. The Accounts table links to customers through foreign keys, allowing one customer to have multiple accounts. The Transactions table records all financial activities, referencing specific accounts. Normalization provides critical benefits for banking systems. It prevents duplicate customer records by enforcing unique identifiers. Account balances remain consistent because they are calculated from normalized transaction data. Referential integrity through foreign keys ensures no orphaned records exist, maintaining data reliability. Consider a real banking scenario where a customer transfers $500 from checking to savings. The normalized database structure ensures this complex transaction maintains data integrity through multiple verification steps, atomic transaction recording, and consistent balance updates across related tables. Banking systems cannot compromise on data integrity. Normalization ensures regulatory compliance through accurate financial records, provides reliable audit trails, maintains customer trust with consistent information, supports risk management with clean data relationships, and enables effective fraud detection. These factors make normalization not just beneficial, but absolutely essential for banking operations. Analytics dashboards represent one of the most compelling use cases for denormalization in modern database design. Unlike operational systems that prioritize data integrity and consistency, analytics dashboards must deliver lightning-fast query performance for complex aggregations and reporting. The fundamental challenge with analytics is that normalized data structures, while excellent for transactional integrity, create significant performance bottlenecks when executing complex analytical queries. A simple sales report might require joining dozens of tables, calculating aggregations across millions of records, and applying complex business logic. Analytics dashboards employ several key denormalization strategies. First, pre-calculated aggregations store commonly requested metrics like monthly sales totals, regional performance, and product rankings. Second, flattened dimension tables combine related attributes to eliminate joins. Third, summary tables maintain different levels of granularity for various reporting needs. Let's examine a concrete example of denormalized analytics tables. Consider a sales analytics system that needs to support real-time dashboards. Instead of joining multiple normalized tables, we create a comprehensive sales fact table that includes all necessary dimensions and pre-calculated metrics. The performance benefits of denormalization in analytics are dramatic. A normalized query requiring multiple joins and aggregations might take 10 to 15 seconds to execute. The equivalent query against a denormalized fact table typically completes in under 100 milliseconds. This represents a 100x to 150x performance improvement, making real-time dashboards feasible. However, denormalization for analytics comes with important trade-offs that must be carefully managed. Data redundancy increases storage requirements significantly. Update complexity grows as changes must be propagated to multiple denormalized tables. Data freshness becomes a concern as ETL processes introduce latency between operational changes and analytical reporting. Modern analytics platforms implement sophisticated data pipeline architectures to manage these trade-offs effectively. ETL processes run on scheduled intervals to refresh denormalized tables. Change data capture systems minimize latency between operational updates and analytical availability. Data quality monitoring ensures consistency across denormalized structures. This comprehensive approach enables organizations to harness the power of denormalization while maintaining data reliability and accuracy. E-commerce platforms face unique database challenges that require a strategic hybrid approach, combining both normalization and denormalization techniques to balance data integrity with performance requirements. E-commerce systems strategically divide their data architecture into two main areas. Critical transactional data uses normalization for integrity, while performance-sensitive data uses denormalization for speed. In the normalized section, transactional data like orders and payments are stored in separate, related tables. This ensures data integrity and prevents anomalies during critical business operations like order processing and payment handling. Normalized transactional data provides ACID compliance, ensures data consistency, prevents update anomalies, and maintains referential integrity, all critical for financial transactions and order management. In the denormalized section, product catalogs embed all necessary attributes for fast retrieval. Search indexes are pre-computed with relevance scores, and recommendation data is stored redundantly to minimize query time during user interactions. Denormalized performance data provides fast query responses, reduces complex join operations, improves user experience through quick page loads, and offers scalable read performance for high-traffic scenarios. This decision matrix shows how e-commerce platforms strategically choose between normalization and denormalization based on specific data requirements, balancing integrity needs with performance demands. Successful hybrid implementation requires careful consideration of data synchronization through ETL processes, strategic caching, read replicas for scaling, event-driven updates for real-time consistency, and comprehensive monitoring to ensure both performance and data integrity. The hybrid approach in e-commerce represents a strategic balance, using normalization where data integrity is paramount and denormalization where performance directly impacts user experience and business success. Implementing normalization effectively requires following proven best practices that balance data integrity with performance. These 6 key practices will guide you through successful normalization implementation. The first and most fundamental practice is to always start with a fully normalized schema. This means designing your database structure to at least third normal form from the beginning, ensuring data integrity is built into the foundation. The second practice is to denormalize selectively and strategically. Only introduce redundancy when you have concrete performance requirements that cannot be met through other optimization techniques like indexing or query optimization. The third critical practice is to thoroughly document all normalization and denormalization decisions. This documentation should include the rationale, performance metrics, and maintenance implications for future developers and database administrators. The fourth practice involves using database views to simplify complex queries while maintaining normalized structure. Views provide an abstraction layer that can present denormalized data without actually storing redundant information. The fifth practice focuses on implementing proper indexing strategies. Well-designed indexes can often eliminate the need for denormalization by making normalized queries perform efficiently. This includes primary keys, foreign keys, and query-specific indexes. The final practice is continuous performance monitoring to identify bottlenecks and optimization opportunities. This involves tracking query execution times, resource usage, and identifying slow queries that might benefit from schema adjustments or additional indexing. These 6 implementation best practices for normalization work together to create a robust, maintainable, and performant database system. By following this systematic approach, you can achieve the benefits of normalization while avoiding common pitfalls and performance issues. Implementing denormalization successfully requires following specific best practices to avoid common pitfalls and maintain data integrity. We'll explore 5 critical practices that ensure your denormalization strategy delivers performance benefits without compromising data quality. The first and most crucial practice is to identify performance bottlenecks before implementing any denormalization. Never denormalize based on assumptions. Always measure and analyze actual performance issues. The second critical practice is maintaining a single source of truth. Even when you create redundant copies of data for performance, there must always be one authoritative source that serves as the master record for each piece of information. The third practice involves implementing robust synchronization mechanisms to keep redundant data consistent. There are several approaches, each with different trade-offs between consistency, performance, and complexity. The fourth practice is conducting rigorous testing to ensure data consistency across all denormalized copies. This requires comprehensive test strategies that verify both functional correctness and data integrity under various scenarios. The fifth and final practice is planning for the overhead associated with managing redundant data. Denormalization introduces additional complexity and costs that must be carefully considered and managed throughout the system lifecycle. These 5 implementation best practices form the foundation for successful denormalization. By identifying bottlenecks first, maintaining a single source of truth, implementing robust synchronization, conducting rigorous testing, and planning for overhead, you can achieve the performance benefits of denormalization while maintaining data integrity and system reliability. Modern database systems have fundamentally shifted away from traditional relational models. NoSQL databases actively embrace denormalization and schema flexibility, representing a paradigm change in how we store and access data. The CAP theorem fundamentally explains why NoSQL databases prioritize availability and partition tolerance over strict consistency. This theorem states that distributed systems can only guarantee 2 of 3 properties: consistency, availability, and partition tolerance. Cloud and big data environments fundamentally favor denormalization due to dramatically cheaper storage costs and the distributed nature of modern systems. Storage costs have plummeted while compute costs remain significant, making it economical to store redundant data. Data lake architectures implement a sophisticated layered approach that balances normalization and denormalization strategically. Raw data is typically normalized for storage efficiency, while business logic layers are denormalized for analytical performance. The contrast between traditional relational databases and modern systems is stark. Traditional systems prioritize consistency and normalization, while modern systems embrace eventual consistency and strategic denormalization for scalability and performance in distributed environments.